All right, so as you mentioned, we're going to jump over to a new set of APIs, which I think to a large extent haven't been explored by most vendors. And it is a capability that we'd like to be able to talk about, one from the perspective of a lot of customers that have been looking at use cases that will utilize this layer, but also from the perspective of how we envisage iOS XR evolving and becoming part of larger scale service provider networks in the future. So the service layer API, as this figure indicates, we're basically going down below the layer where the application and the control plane stacks exist. So visualize a network OS stack. You have BGP, OSPF, ISIS, whatever running on your box. And at some point, these protocols are interacting with the underlying infrastructure, right? RIB, the label switch database, the components such as BFD, which need to be able to get notifications back to the protocol stacks. So in a way, there is an API that these protocol stacks use to be able to interact with the underlying infrastructure and the hardware. And one of the main goals with the service layer API is to be able to expose that layer directly to the user. And I'll get to some of the use cases that sort of talk about why we're even doing this. The use cases have been evolving. We've been working with a lot of large-scale service provider customers, and some of them have pretty sophisticated requests primarily because of what their core focus is. And let me maybe just put down the disclaimer that when we talk about most of these customers, the network is really just the plumbing infrastructure for them. Their main focus is the applications that run on their data centers, the traffic that they're able to go ahead and send across the network. But the network basically needs to behave in the right way for their applications to reach their end clients properly. And for that primary reason, we've seen a lot of different use cases evolve where these customers don't go with a normal network deployment strategies. They're not going to go ahead with validated designs that work everywhere because they have their own design considerations based on the type of applications that they're working with, based on the way their networks are architected to deal with the outside world, etc. So let me look at one such use case. You can consider CDN POPs. There are a number of customers that deal with having, let's say, a single router that communicates with a bunch of host machines in a given POP location. And you can have multiple such POPs across the entire country, right? Now, for such customers, the ratio of the number of network devices to the host is actually pretty high. You're not talking about like a huge number of host machines behind a given router or switch, right? So with that in consideration, as they have to scale out with a large number of POPs, the network device cost really does play up in the way they design the network. And for that reason alone, a lot of them have looked at being able to either reduce TCAM usage so that they can either get smaller form factors of these devices deployed in the POPs, or at least have more control over how the routes get downloaded into the RIB and eventually the FIB. So in this case, we explore one such use case where you've got, let's say, a bunch of different providers that the router communicates with, but at the same time, you have a separate BGP stack, which is either running on a host machine, or it could run as a container on the router itself, which is able to get routes from a variety of different pieces in the infrastructure. But you effectively put a controller or agent in between them so that you programmatically determine what routes go into the RIB. And this has a lot of effect on how many routes get downloaded into the RIB and FIB, and consequently the TCAM usage and hence the cost, right? So this is primarily a cost-driven use case, which you see because, as I mentioned, because of the device to host ratio. And we've got other use cases, right? Traffic engineering, path selection is kind of obvious, but in doing so, a lot of customers need not want to depend on vendor-driven policy architectures to be able to determine how or why a given packet should take a particular path. So a lot of this logic can either be centralized, it could be distributed, and I'll get to that. But in essence, being able to override what the current routing infrastructure is doing, just so that your application can have the right path through the network, is pretty much critical to most of the large-scale service providers that we're dealing with. The way they deal with networks is that, just like server infrastructure, network infrastructure is bound to fail at some point, right? If it does, or there is congestion at any given point for application traffic, you need to have the control to be able to redirect application traffic at whim. And in this case, we're looking at a situation where the controller can have the necessary logic to detect not only the applications running on the host machines, but also the current telemetry data coming on from the network devices to go ahead and program the path that the device needs to provide for the path. And in this case, therefore, giving access directly to the RIB or the label switch database becomes absolutely crucial. Remember, the logic for what you need to do to determine the path exists in the controller and not in a feature provided by the vendor. Right? So that is sort of how we're looking at this. And then bringing your own protocol agent. And this is actually not a use case that is just for certain sophisticated users. We've actually seen a lot of requests come in from customers in the service provider space where they want to be able to enhance router functionality, the routing protocol functionality, without having to wait for release timelines for whichever vendor they work with. And in this case, examples would include maybe getting your own custom TLVs in ISIS to be able to communicate certain parameters about your devices so that the correct paths are selected across the network. And in this case, what you're seeing is that most of the logic of how the routing influence actually occurs is concentrated in a distributed form factor. It's not in a controller. So we haven't really pinpointed controllers as the only way in which you would want to be able to control using this API. Distributed agents, distributed protocol augmentations, etc. on your network are an equally important way of being able to handle this API layer.
So
yeah,
one of the things that I'm missing, I'm really understanding the whole API-driven and access, using the API to do stuff like bring new protocols or enhanced protocols or proprietary protocols that you create as a service provider to your network. What I'm missing is the connection between something like OpenConfig and embracing and contributing to OpenConfig and the connection to the value prop of Cisco. Because one of the traditional messages from Cisco is that all Cisco solution is normally the best solution. I'm thinking, you know what, I can build this with white boxes and my life would be very easy because it's cheaper and easier to manage. Can you help us understand the value prop of why Cisco is why OpenConfig combined with the hardware platform is a better solution or better approach?
Right. So in a way, I think the core aspect here is that the right thing to do is whatever the customer wants to be able to do to get their business up and running properly. And in our use cases, OpenConfig is a good example, right? OpenConfig is basically an abstraction, an API definition that comes in from our customers. There is a big difference between a vendor pushing their own API model and their own API representation and indicating that it is the best way to be able to do a certain task. But in service provider environments, you typically work with a lot of multi-vendor environments, right? Every vendor providing their own API really makes it hard for all the developers and the network operators to be able to operationalize their network easily. What they're really looking for is consistency, right? And while standards are great, everyone has different implementations of the standards at a given point in time. So OpenConfig has been great in the sense that it is our customers that have basically defined the architecture for what the API needs to look like, and they've given it out to the vendors to implement, right? So we're basically implementing what the customer wants and not necessarily what the standards dictate, right? And in that sense, Cisco effectively is providing the infrastructure to get the customer to be able to use those APIs. And the way we are able to provide enhancements to the APIs that already exist, the way we're able to update our protocol stacks and new APIs at lower layers that can allow customers to do more, that sort of helps us differentiate with respect to other vendors, even if the API layer becomes more or less the same. APIs only determine what how you can go ahead and program the features. It doesn't necessarily determine what features you support, right? So as long as we continue to support all the features that our customers need, and we provide vendor agnostic APIs for them to work with, I think we're pretty much giving them what they want.
And in the Cisco solution, you've got Cisco Tech behind you as well.
Yes. Yeah,
Whereas
exactly.
if I rolled a white box solution, I may not have the support backing it as I would with a Cisco solution, maybe.
Absolutely. So support plays into it. A lot of external agents and software that we build out play into it. So I think the core aspect here is that we need to be able to give the customers what they want, but add on top of it as necessary. So as just harking back to what I was indicating earlier, all of the different use cases that you saw were fairly sophisticated, but at the same time they were accessing a layer that is disjoint from how the generic protocols or management layer APIs would allow them to work with the network. So the service layer APIs effectively give you access to the lowest network infrastructure in the router. It gives you access to the RIB. It gives you access to the label switch database. It gives you access to BFD. It gives you access to the interface notifications, right? And the core aspect here is that I will be able to override what my network does pretty much at the behest of my application, right? And that is the core aspect of how we want to look at the use cases that this API layer will define. So let's look at the case for service layer APIs, and let's make a case for it. So we've got extremely high performance that we're able to glean out of this API. This is crucial to understand. Having a management layer stack in between the API and what the router can do has some impact on the performance. And a lot of the requirements around controllers as well as agents in this space require extremely high performance requirements between the controller agents and the router. And for that reason alone, this API going directly into the network infrastructure layer with the right transport, which I'll talk about, effectively gives you the highest performance that you can get. As an example, we've seen varying levels of route programming capabilities into the RIB, ranging from 25,000 to 50,000 routes per second purely through the software. And that is huge. Okay, being able to do that at a higher layer is just not possible. So performance is a key factor in terms of how we enable this particular layer. API for the do-it-yourself system is, I think, something that's pretty obvious based on the use cases I spoke about. Customers want to be able to control more of what their logic is on top of the network infrastructure. So they can bring their own protocol, whether it's on-box agents or it's controllers. They can use that to influence routing decisions to override what the current infrastructure is already doing. And in doing so, they can accomplish all of this over gRPC, which is the transport protocol that we're using. And lastly, you want to be able to offload the lower level tasks to XR. So the core part of this is that in the end, all of the capabilities for the do-it-yourself systems require intensive amount of logic to be able to implement them. But higher scale as well as conflict resolution requirements at the lower layers is something that customers might not want to implement. And for that reason alone, we basically allow the service layer to exist at a level where most of the scaling as well as the conflict resolution is handled for you, and you basically get access directly to the infrastructure layer directly. So keep these three things in mind based on how we're looking at the use cases for service layer APIs. And therefore, in order to build the service layer API for these use cases, we took a three-pronged approach. One is we had to make sure it's model-driven. I think we've already articulated why model-driven APIs is basically the only way we can scale out and version these APIs consistently. So in this case, we use protobuffer IDL to be able to model the API. And more such modeling IDLs may be possible based on that extraction. In addition to that, RPC support is essential. I've spoken about use cases where the agents can go in controllers. They can also go on routers directly. So if you have an RPC mechanism, both of these are possible. right? We've seen certain other vendors try to approach this without building an RPC, and it just doesn't solve a lot of the use cases that you would want. So having a model-driven API with an RPC is sort of the ideal way of building out this API layer. And a layered approach is good. A true focus on what the API is supposed to do without trying to pollute it with higher level API constructs around protocol stacks is great, because it gives the customer exactly what they want and nothing more, right? So they get their own logic, fit it on top of the infrastructure, and just works. So keep the model-driven approach combined with RPCs, combined with the layered architecture in mind, because this is basically how we define what the service layer API can do.
So
yeah.
Some people are really opinionated with the API-driven approach, saying, you know what, going back to the previous slide, RPC versus API. So a lot of times it's an RPC versus API. You're either all in one bed, or you'll expose some APIs via SDK, which it seems like you guys are doing, versus saying, you know what, we'll dog food our own stuff, and it's all just API. Right. Can you talk to why that decision is made to still say, okay, there's some RPC support and where you've seen that fail in the markets, because I'm losing some context?
Sure. So from the RPC perspective, what I'm really trying to pinpoint is that you could build out this SDK in such a way that your agents can only run on Box, because that's where the library is, right? So I have to have code written in the same language, integrating with the same library on Box. But as soon as I put in an RPC, I'm agnostic potentially. If I choose the right RPC, I'm agnostic to the language that I use, right? Because I can create the bindings in whatever language. Mm-hmm. And whether I run on Box or off Box, my client works in exactly the same way, right? It's just the IP that it needs to connect to. So in a way, you're providing a lot of consistency in the way in which you can create clients for the servers running on the router, right? So that, I think, is probably a core part of why RPCs are important, not only at this layer, probably at every layer going upwards. And that is also a reason why we use gRPC, by the way. It's based on the HTTP2 transport, is pretty mature, and is sort of proven to be highly performant for most of these use cases. And there have been some attempts on this layer earlier, but gRPC sort of proves how this layer could actually become real. So quick intro, this is kind of how we build it out. We have a bunch of different functionality verticals that we define in this system. Primary ones that you'll want to consider are the RIB RPCs, the MPLS RPCs, and the interface RPCs, right? So the RIB RPCs allows you to push whatever set of routes you want at very high scale and rate, IPv4, IPv6, and also get notifications on the routes that are already within the system and how they're changing. MPLS RPCs allows you to effectively program the label Swiss database, create a label to prefix mapping, thereby creating traffic engineering layouts in the way you want. And there are going to be more things coming with SRTE applications at this layer. And interface BFD are typically used for notifications back into the controller or the agent, so that you can assess what the network is actually doing during your operation and then adjust accordingly. So this sort of goes over it again. I'm going to skip to that and quickly look at the demo. So I spoke about a few things initially from the perspective of why the service layer APIs are important, right? We need performance, we need flexibility so that you can bring your own custom logic, right? And we need to be able to allow the agents or the controllers to offload certain tasks to the XR stack. This allows them to scale a lot more and concentrate mainly on the use case that they have. So in this case, what we have is basically a couple of routers. They're running IBGP between them. And all the routes from router 2 are being learned by router 1. Now, on router 1, we have a single route policy that says drop all the routes. The reason we want that is because we want the routes to be processed at the controller layer and not at the device layer. The way we're able to achieve that is through a pretty well-known protocol called BMP. And BMP protocol basically says that my adjacency in RIB of BGP, which appears before the normal RIB, will be streamed out to an external receiver, even if you drop all the routes in the local RIB. So that's what's happening here. So I'm learning routes from router 2, and it is being sent to the OpenBMP collector and then into the controller directly over a message bus, right? So that's the architecture that's taking place. And as soon as I've done that, there is a crucial thing to understand. I have basically taken the RIB manipulation exercise out of BGP and given it to the controller to handle. So BGP still creates neighbors, it still learns routes, it still distributes routes to other routers, but the RIB manipulation is handled in the controller. And that allows me to be very flexible with respect to the number of routes that I want in the router, the kind of routes that I want in the router, and also the sort of path selection and routing policies that I want to apply to those routes.
So I no longer have to configure prefix lists or route maps or anything on the router.
Yep.
That's all handled in the controller.
Exactly.
And when there's a change to my policy, that's not going to affect my neighbor relationship with that peer anymore, right? I don't have to clear it.
No.
Or have route refresh capabilities or any of that stuff.
Yeah, exactly. And it's a use case that I'm trying to basically push forward. There are some customers doing this, by the way, right? And this gives them a lot of flexibility in the way they handle the routes in the system, right? And they can make this box as cheap as possible with the lowest TCAM size, because now they control the number of routes that go in. Yeah. You don't have to put the entire internet routing table in there, right?
Yeah.
So that becomes one of the core aspects of it. And another thing to understand is that because this is a highly performant channel over gRPC, the entire system operates as if it is a single logical entity. So when route updates come from router 2, it isn't as if the controller might miss some routes. It won't, because the routes come in over BMP and they're immediately pushed down through programming over the SLAPI channel into router 1. So you have a system where the entire controller plus router combination is acting as a single logical entity responding to all the routes coming in, right? And that's primarily because of the sheer performance of the channel that you get with these service layer APIs. All right, so this here is my router 1. And what you will see here is, do I need to increase the font? Okay, so here I have BGP configured with respect to router 2, but what I will find is that there is the only routes that I'm learning over BGP are from an eBGP peer and not an iBGP peer, right? So I have 2 routers pairing with this router, and only the eBGP routes are pushed in, primarily because I have a single route policy here on my iBGP peer which says just drop all of them, right? So that's kind of what's happening here. And as that takes place, you can see the eBGP routes in the routing table. Now, in addition to that, what I will do is I'm going to jump over to my controller code. And by the way, all of this is on GitHub, so it can be looked at later. Okay, so if you just saw, I ran my controller, and what it's really doing is it's fetching all of the routes that are coming in from router 2, and they're being detected by the controller and they're coming in, right? So it's populating the RIB externally.
If you can make the font a little bit larger.
Thank you.
Thank you.
Sorry. All right, so if you see, these are actually the prefixes that I'm learning from my iBGP peer, and they're all coming into the controller. So this is coming over the message bus that I just indicated earlier. And what I can now do is, because I'm running my controller, it actually publishes all of the routes after manipulation into a single message bus. So I'm going to go ahead and
What device is this that you're on there?
So right now I'm going to hop into my Ubuntu instance where I will be running my service layer API client. Okay. This is going to connect to the message bus and then push the routes into the router.
Okay.
Okay. Okay. If you can see, I just had an add success. Let me increase this font if you can see it. Basically, all of the routes came in from router 2, went into the controller. It got the routes over a message bus. It manipulated the routes, created the final rib that needs to go into the router. And the service layer API client picked those routes and is now going to push them into the router over that performance channel. So what we have in the end is when I jump into this router, look at the routing table right now, and let's look at what happened now. So what you have is a bunch of application routes that were created by my controller. And these routes basically respond to all the events in my network, because the entire system becomes a single logical entity. So if I go ahead and remove routes on router 2, these routes get pulled out. If I put them back in, these routes come back. So just the last part of the demo.
So those application routes are BGP routes that are coming back from the controller.
Those application routes are effectively created by the controller with the correct admin distance to match what BGP would have created.
Yep.
And they've been pushed into the rib. So the rib will continue to do conflict resolution. You can still have other existing protocols in the system, and the controller just becomes another protocol, right? It's behaving just as if I would run ISIS on the system and how it would try to program the rib.
Yeah.
Right, so.
And maybe I missed this. What is the controller?
So the controller is completely open source. I've written a Python-based controller that basically runs an OpenBMP collector and accepts all of the data over a Kafka bus.
Okay.
Okay, so it's a message bus architecture that
It's
exists.
homegrown.
It's homegrown. This is just an example of how you can do it, right? And lastly, let's just get into the second router, which is the one that is actually sending the routes in. And I'm just going to go and I will remove all of the networks that it is currently advertising just to be able to create an event in my network. Now, BGP has its own cycle, update cycle, right? So when the next update cycle comes in, what router 2 is going to do is it's going to pull out all of the routes that it is publishing to router 1. And when that happens, the controller is going to detect it over the message bus. The service layer API client will again detect the local rib over the message bus and will remove those routes from router 1. Right? So the entire system is behaving as if I'm running a single BGP protocol directly peering with router 2. So, okay, just want to wait for, it happened. So as you can see, all the routes are pulled out, right? Because I removed the networks that are being advertised by router 2. And therefore, this sort of helps us come back to what I was indicating earlier. We've shown how you're able to create a single logical entity because of the high performance. You get complete flexibility in the way you design your logic on what your network is supposed to do. So you can have your own user-defined route policies. You can have your own path selection algorithms. And you have complete access to them if you use the right protocols, in this case, BMP. And bear in mind that when I constructed the controller, I did not have to worry about being able to do conflict resolution of routes with other protocols interfering with me. My controller is not the BGP speaker. The router is, right? So the controller only handles the rib, and it does what it's good at, which is manipulation of the rib purely as a data problem. It's not a protocol problem, right? So this is one example of how our customers like to be able to get full control over what they do on the network.
So you said that router can be a much less expensive box now because it doesn't have to do a lot of that stuff, or a lot of what it would normally do, all the route policy and the filtering and whatnot.
Yeah.
But let's say that BGP table coming in, if that's a full BGP table, it's still got to be able to handle taking all of those prefixes and then
absolutely
sending them over. So you still got to have some juice in that box.
No, on this guy, yeah, sure. I mean, but it's there's a big difference between the software handling those routes and the hardware having to handle those routes, which is where the cost really comes in, right? Yeah. So the software is much more scalable, even if it's on a slightly less capable box, because in the end, if you get CPU memory disk that's enough for the software, it'll work.
Yeah.
You don't need TCAM space, etc. on it.
Yeah.
Right? So that's one of the major use cases that sort of comes out of it.
Yeah.
So just quickly wrapping up, We spoke about manageability at a higher layer and how that allows people to interact with what iOS XR has to offer in terms of features, in terms of all of the goodies with respect to the models, etc. And the service layer API is basically allow them to go directly into the network infrastructure layer and provide their own custom logic to be able to make sure that the network operates in the way they want. So it's really about a lot more flexibility, but in the end, we're talking about a layered architecture of APIs with APIs being model driven at every layer. That is the only way we're architecting our APIs. No API layer is coming in without models. Okay, so that pretty much wraps up. These are some of the most important resources that you might want to look at. ydk.io for everything that Santiago indicated earlier. YDK is the abstraction that helps you get bindings on top of all the models in the manageability layer. And take a look at the XR docs content on Cisco service layer. It will give you all of the API information as well as pointers to other things that we've released with the service layer.